grab a beverage.
Great. All right, hello everyone. Thanks for attending today's CGD seminar. Before we get started, I'll remind everyone of our CGD code of conducts at these seminars, where we share the air, acknowledge teamwork, encourage innovation, show appreciation, consider new ideas, and offer constructive feedback. I'll also ask that everyone please keep themselves muted during the talk and hold any questions until the end. If you have any clarification questions, you can put them in the chat and I will ask the speaker. Now it's my pleasure to introduce today's speaker. Seth McGinnis is an Associate Scientist 4 in the Risk Group in RAL. He received bachelor's degrees in Earth, Atmospheric and Planetary Sciences and Physics from MIT, and a PhD in Geophysics from CU Boulder. His work focuses on issues affecting the practical use of model output by non-specialists, including as the data manager for the NARCAP and NA Cortex data collections, where he works with output focused on regional climate change in North America. His talk title today is Climate Change and Simultaneous Megafires in the Western US. So Seth, feel free to share your screen and take it away.
All right. All right, you see my slides?
Yep.
Okay, great. So good morning. I'm going to be talking about wildfire today, and you know, of late, it doesn't need a whole lot of motivation. But this is this here is a screenshot of the fireweatheravalanche.org website from October of 2020, showing all the wildfires in the Western US that were burning at that time. There are at least 10,000 acres in size. And this was the time when the East Troublesome and Cameron Peak fires in Colorado were burning and, you know, turning the skies yellow with smoke and things like that. So wildfire, it's you know, pretty relevant to everybody. In terms of fire management, fighting many large fires simultaneously is harder than fighting just one very large fire. This is a sort of a diagram. On the left, we've got one big fire. On the right, we've got a number of smaller fires that have the same total area. But the important thing is that you fight a fire on its perimeter. And so if you have a greater total perimeter, if you've got more fires, that's more perimeter, and that's a longer fire line. You also have to consider issues like traveling between incidents and moving resources around, which is lower efficiency. And it just means that, you know, overall dealing with the fire means there's a lot more variables and decisions to make when it's multiple fires than if it's just one gigantic fire. Moving into the future, it's not obvious what effect climate change is going to have on the number of simultaneous very large fires. You know, wildfire wants hot weather, it wants lots of fuel, which is vegetation, and it wants that fuel to be dry. And our future climate is going to, you know, there's a lot of unknowns, but consistently, hi cat, consistent results include that average temperature are higher. With higher temperature, you get more moisture because of Clausius clapeyron, and many models show greater extremes of one kind or another. And these can push in both directions in terms of whether they're going to make wildfire more or less of a problem, because, you know, more moisture sort of represses the dryness of the fuel, but it also can lead to more fuel growing in the first place. And so there's a lot of big uncertainties about what's going to happen. What the effects of climate change will be on fire. Some regions are already showing changes in simultaneity of these very large fires. These are plots showing the average annual number of fires burning per week in different regions in the Western US. And you can see that a number of them, the Northwest, the Northern Rockies, Rocky Mountain, all have sort of fairly clear upward trends already. And this is just in the observed record. So the question is, and how do they compare with the uncertainties that are associated with different climate models? Our group, which is the risk group within NCAR, Linda Mearns, Melissa Bukowski, me, and Lee Kesenick, we have the NSF growing Convergence Research program has funded a multi-institution collaboration that we are part of to look at this question. It includes us. It includes a number of folks from University of Washington, including Alison Cullen and Susan Pritchard. We've got John Abatzoglu from UC Merced. And we've got a bunch of stakeholders from a number of different agencies, including the Forest Service, Department of the Interior, Bureau of Indian Affairs, the nature and non-federal agencies too, including CAL FIRE and the Nature Conservancy and so on, working together to study this question and looking at a lot of different aspects of the question. Convergence research, and this is NSF's definition of it, integrates a bunch of different disciplines around a specific problem. So the problem we're looking at is we are looking at, you know, what's the effect of climate change on simultaneous megafires, but that also includes looking at policy and land use and what happens with fuels and what happens with where people live and things like that. And so beyond just looking at climate change and fire, which is what I'm going to talk about today, this project also has a lot of integration with stakeholders and we've been working on doing iterative co-production of knowledge with them. It's got to focus on decision-making and on fire management resources and on ecology and land use. So the part that I'm talking about today is just one part of this bigger convergence project. So what our approach is to looking at the effect of climate change on simultaneous megafires is that we have been using generalized linear models to relate the number of fires, large fires, that are happening simultaneously at the GAC level to fire indexes that we calculate from climate data. And a GAC is a geographic area coordination centers. And these are administrative regions that are used for fire management. So, you know, the Northwest is sort of mostly Oregon and Washington, and they coordinate within that GAC how they're going to use different resources and how they're going to fight fires and things like that. And so these are all the regions. And we're only at the moment looking at simultaneity within a single GAC. Looking at, you know, simultaneity across different GACs and how that affects resource sharing between different regions is a separate problem that we haven't tackled yet. We have to tackle this problem first. So that's roadmap of what I'm talking about, is how we build these generalized linear models and what they tell us about what's going to happen in the future. So the data we're using to build our statistical models, we are using observational data from GridMet, which is a gridded observational product of climate observations. John Abatzoglu is the lead on that project. That gives us climate data that we can calculate fire indexes from. And then we use the MTBS, which is monitoring trends in burn severity catalog, for lists of historical occurrences of fires. And this figure here shows you the CONUS GACs, and overlaid is all of the fires that were at least 1,000 acres in size that happened between 1984 and 2016. And that's what we're calling a megafire, is a wildfire that's at least 1,000 acres in size. We found in our early research that the models performed very poorly on the eastern and southern GACs. So we've dropped those from our current analysis, and we're just looking at the western part of the US. And you can see there's seven different regions here. And you know, the fires have a lot of spatial variability within each region, but they're pretty dense throughout. So that's the observational data you're using. For future data, and climate change projections, we're using regional climate model simulations from Cortex, which is the Coordinated Regional Downscaling Experiment, which is a big program to do dynamical downscaling using regional climate models of simulations from the CMIP5 archive. And you can see the North American Cortex domain on the right. There's 14 Cortex domains covering the entire world, and there's bazillions of simulations that people have done from many different institutions. We have an archive of Cortex simulations for the North American domain here at NCAR that we built. It's at the website na-cortex.org. This was funded by Department of Defense's ESTCP program, and the goal is to build a data archive of these simulations for climate science, but also for decisions making and impacts users. And the goal was to make it usable by people outside of climate science, to make data accessible to non-specialists. It's the North American branch of the Cortex program. We've got 7 regional models, downscaling 7 different global models in varying combinations under 2 scenarios, or 2 different RCPs. Simulations are at 50 kilometers and at 25 kilometer resolution, or half degree and quarter degree, which is equivalent. The archive has daily data from 1950 through 2100 for a lot of variables, in particular, including the big 7 impacts, climate impacts variables, precipitation, temperature, Tmin, Tmax, surface winds, incoming solar radiation, humidity, and I think that's everything. And we also have a bunch of derived data products, which include bias-corrected versions of the data, data that's been pre-aggregated to different timescales, data that's been interpolated onto a common grid, and so on. For this work, we're using 13 simulations. This is the matrix showing the combination of all the simulations of RCMs in the rows and, sorry, GCMs in the rows and RCMs in the columns. 13 different simulations, all under the high emissions RCP 8.5 scenario. In each case, we used the highest resolution available, which in most cases was 25 kilometers. But there's 3 of them that were only available at 50 kilometers. So we've got a good spread of models, and they also do a pretty good job of sampling the range of equilibrium climate sensitivities that are seen in the entire CMIP5 ensemble. So it's a good spread of simulations in terms of showing different possible outcomes given that scenario. To use them in a climate impacts analysis like this, you really want to do some bias correction of the data, because regional climate models, all climate models, tend to have biases in them, systematic biases in them. And so to correct that, we have used a multivariate method developed by Alex Cannon called MBCN, which is pretty clever. It's an application of a method that was developed actually for image processing. And it turns out this problem is equivalent to the problem of color correcting film to match a particular color profile. And a very hand wavy, skipping over the details way, how this works is you take your data with a bunch of different variables, you apply a random orthogonal rotation to the data, you bias correct each of the resulting dimensions independently using quantile mapping, and then you undo the rotation. And then if you iterate that many, many times, clever mathematicians have shown that that is guaranteed to converge not just the correct marginal distribution, but it also fixes up all of the relationships between the variables as well. So it corrects the intervariable distribution as well. We've applied this bias correction to the entire NA Cortex data catalog in our archive, and it's all published and available, using 2 different observational data sets. One of them is GridMet. GridMet only covers CONUS, but it does include precipitation, Tmin, Tmax, humidity, incoming solar radiation, and surface wind variables. We've also done it using DayMet, which is a different gridded observational data product. DayMet covers all of North America, but it does not have winds in it. And winds are important for some of the fire indexes that we wanted to calculate for this. So we needed to use GridMet instead of DayMet. And from the bias corrected data, we have calculated 7 different fire indexes. We've calculated both of them, both for the observational data and for the RCM simulation outputs. We calculated KBDI, Keach-Byrom Drought Index, Canadian Fire Weather Index, Modified Fosberg Fire Weather Index. FM100 and FM1000 are 100-hour and 1,000-hour fuel moistures, which are measures of how fast fuel of a particular size, sticks of a particular size dry out. And then energy release component and burning index are 2 fire indexes that are often used in fire management. We calculated 2 different variations of those using different assumptions about the fuel models behind them. Lee Kesenick, who is an associate scientist 1 in our group, wrote NCL code to do all of these calculations. And that code has been published in a GitHub repository, an NCARD GitHub repository, if anybody wants to use it. And this is just, this figure is just showing an example of what 1/4 degree Canadian Fire Weather Index looks like. You can see that there's a lot of spatial variation depending on terrain and things like that. And this is just showing it for 1 day. Okay, so that's all the data we've got. And the way we're putting it together is that we are building statistical models using a hurdle GLM with a negative binomial response. Simultaneity counts are zero inflated and heavy tailed, which you can see from the distributions here. You know, the tails stretch off quite a bit off to the right on each of these histograms. And I'm not even showing the zero counts here. Those are indicated by the little boxes up here. The shaded part is how many non-zero instances we had of simultaneity, and the open part is what percentage of days were no simultaneity at all. No fires of at least 1,000 acres in size. And you can see there's a lot of zeros here. So the hurdle model is a statistical model that's got two parts. One part tells you whether the data is zero or not zero. And then there's a second part that tells you what the count is when the data is not zero. The hurdle part of it, the zero non-zero, handles the zero inflation. And then using a negative binomial for the count part handles the heavy tail a lot better than a Poisson distribution would. So that's the statistical model that we're constructing to relate how many simultaneous fires are happening within a GAC to fire index values within that GAC. Now we have to do something to sort of harmonize the climate data with the fire data. The fire data, we're looking at the count of big fires within a GAC, which is a large spatial area. And the nature of the reporting on the fires and when they're happening, and the nature of the decision-making around how these fires get fought and things like that is managed, I should say. Makes it so that bi-weekly is really sort of the right time frequency to be dealing with the fire data, whereas our climate data is either 25 or 50 kilometer grid cells, and it's daily. So we need to aggregate this data in some way to get those two things to match up. So we averaged the data, averaged the fire indexes over the entire GAC. We tried a couple other things, but it turned out that just averaging it over the entire GAC worked the best. And then we used 5 different ways of aggregating it up from daily data to 2 weekly data, which we used a 2-week running minimum, maximum, average, 20th percentile, and 80th percentile. So we tried an array of different ways of doing the time aggregation on this. And then to find the best predictor for each region, we fit a generalized linear model. We fit 90 generalized linear models for each GAC. That's the 9 different fire indexes, 5 different time aggregations, and 2 different spatial aggregations, because we wanted to make sure that it would work both on the coarser resolution RCMs and finer resolution RCMs. So we fit all of those. We did an 11-fold cross validation on the fitting, which is we had 33 years of observational data, so that's 10 years of training data and 3 years of holdout data to make sure that we're getting reasonable results out of these things. And then we can pick out the best predictor for each GAC based on the AIC weight, which is the Ake information criterion. And so, here at the right is a figure showing some of the evaluations that we did to sort of check that they were producing reasonable results. You can see the performance on a precision recall curve is pretty good. We used that instead of a receiver operator curve because that works better when you have unbalanced when your classes are not balanced. If you've got a lot more zeros than you have non-zeros, a precision recall curve works better than an ROC curve. And the mean square error on the cross validation is pretty reasonable looking. And the AIC weights were able to pick out a pretty clear winner in pretty much each case. So we fit all of these statistical models. We picked out the best predictor for each GAC. And then here's a figure, I produced some validation plots to make sure that the sanity check the results, make sure they made sense. So the top figure is showing the blue dots are the actual observed simultaneity for the Great Basin GAC using the best predictor. And the the black line is the predicted mean amount of simultaneity. You can see those line up pretty well. The middle panel shows the probability of non-zero simultaneity, and the little rug plot at the bottom shows when the simultaneity was happening. Those line up pretty well also. And then, down at the bottom, this is the probability of getting a particular simultaneity level or lower. And again, the little white dashes are where the simultaneity was happening and how much of it. So, we get 30 when the probability of getting 30 is pretty high, and so on. So great, these results look reasonable. The statistical model is doing a decent job of reproducing the results. And so what we found is that for most of the Western US, the best predictor was area average, 2-week average Canadian fire weather index. That's for Northern California, Southern California, the Great Basin, and the Northern Rockies region. In the Northwest GAC, it was 80th percentile Canadian fire weather index, but 2-week average was, second runner-up. So these guys are all pretty similar. In the Rocky Mountain region and in the Southwest region, instead of Canadian fire weather, it's 100-hour fuel moisture. And the difference between those two is that 100-hour fuel moisture only takes in temperature, precipitation, and humidity as inputs. Canadian fire weather also considers winds. And of course, we're not resolving the very extreme winds at 25-kilometer resolution, but spreading due to winds is a pretty major factor in wildfires in California. And also, the Canadian Fire Weather Index was developed for Canada. So the fact that it works pretty well in the northern part of the US is not surprising. And also in the Rocky Mountain, in mountainous regions, which are high elevation, even though they're further south. So it sort of makes sense that this would be a good predictor. And it's also worth noting, in all cases, we found that the best predictor was the same at both, 25-kilometer resolution and 50-kilometer resolution. So great, we got pretty consistent results. That's good. So now what we did is we took the statistical models and said, okay, we've built a statistical model that relates the observed simultaneity to the observed climate data. And then we take climate data from our simulations and provide it to the statistical model and get out predictions of distributions of simultaneity. So this is, again, just a validation plot of like, okay, what does my statistical model say when I push some RCM data through it? Does it make sense? Yes, good. We see annual spikes in the predicted amount of simultaneity and when it's happening, and those plots look sensible. So that's good. There were some early stages where these results did not look good, so it's important to make sure that they are still producing sane-looking results. And so then to analyze the outputs, for each GAC, we found the historical 5-year return level. We use that because there are different preparedness levels for firefighting within the GACs. And the maximum preparedness level is called PL5, preparedness level 5. And in at least one GAC, we heard from the stakeholders, that's based on conditions that are seen once every 5 years on average. So a 5-year return level is not exactly the same as what they're using to decide their preparedness level. The 5-year return level of simultaneity is not exactly what they're using. They're also considering a lot of other things like characteristics of the individual fires and, what's the availability of resources for a variety of reasons beyond just how big the fires are and how many of them are. But it's at least in contact with the criteria that they're using for the decision-making about how they're going to use resources and things like that. So in each GAC, we found the 5-year return level, and the analysis I'm going to show you now is based on what's the probability of exceeding that historical 5-year return level for each different regional climate model simulation. And all of the time series I'm using here are biweekly, so that's worth noting. It's also worth noting that these 5-year return levels vary quite a bit depending on which GAC you're in. You know, in the Great Basin GAC, it's up here at about 40 some, and in California, it's only at about 10. Most of the others are at about 20. You know, the Southwest, Northwest, and Southwest, Northwest, and Northern Rockies are up in the 20s. So that's what all of the subsequent figures I'm going to show you are based on. So let's start with the Great Basin GAC. This consists mostly of Nevada, a good chunk of Utah, and southern Idaho. You know, some beyond that. And this is an area where there's a lot of wildland where fires don't necessarily get fought because, you know, it's out in the middle of nowhere. Nobody lives there. There's no towns. There's no significant resources of value. So there's many wildfires that they just allow to burn in this region. And so this has a lot higher counts of simultaneity than many of the other regions do. What we're showing here, the top panel is a box plot showing rolling 30-year averages of the probability of reaching that 5-year return level. So those are the individual values going into each box, and then there's 13 of them, one for each RCM. So this is showing you how the projections of the different climate models vary over time as we move from, you know, the historical period through the 21st century. The bottom box plot shows you the seasonal variation of simultaneity. So blue in this box plot is the historical period 1980 to 2010, and then red is future period 2040 to 2070. So you can see the change from historical period to future period. And then the little X's are the mean value. The box plots, you know, are the usual median, interquartile range, and then I think it's 5th and 95th percentile on these ones, and then any outliers. So what we see looking at the top one is that there's a clear upward trend in this region throughout most of the 21st century. You know, the probability of reaching 39 simultaneous very large fires in this region goes up from a few percent up to, you know, 6 or 7% in the median of the ensemble by, you know, nearing the end of the century. So there's a fairly clear upward trend. Spread between the models also is relatively large and gets bigger over time. And there's a fair amount of multi-decadal variability, which is sort of the, you know, how much the median varies from box to box. So that's sort of the general picture that we're seeing in this Great Basin region. In terms of what the seasonality of simultaneity looks like, you know, we've got our blue boxes here show us what the historical seasonality looks like, and then moving into the future, you know, the season doesn't get much. The season doesn't change very much, but the amount of simultaneity you get at the peak of the season goes up by quite a bit. So that's a pretty straightforward picture for the Great Basin. In the Northwestern GAC, the overall pattern looks pretty similar. Note, however, that the vertical scales here are pretty different. Here we're going from, in the Great Basin, we're going from 1% up to 10%. Here we're going from 1% up to about 16%. In the Northwest, it's starting out with a lower amount of simultaneity. So the relative increase here is higher. You know, it's going from just a couple percent likelihood in the peak of the season of hitting, what is it, 26 is the threshold, is the 95% return level in this region. You know, that bumps up to about like 7% for the ensemble mean in, you know, the 2060s or so. So that's a pretty significant increase in the probability of like very high levels of simultaneity for this region. The Northern Rockies region has an even bigger and more dramatic increase. The scale here is going up quite a bit, and looking at the seasonal plot, in late August, I think this is the future mean is about 4 times what the historical mean is in terms of probability of hitting that 95th percentile simultaneity level. So that's a really big and dramatic increase that we're seeing in North Dakota, Idaho, Montana area. Moving into the Rocky Mountains, where we live, familiar to all of us. Here, the increase over time, over the century, is not as dramatic. It does definitely go up, and it's still got that spread of the different models increasing also. But what's interesting here is that we see the season getting longer to some extent. So you can see that, it's sort of, in the historical period, it's sort of dropped off almost entirely by, I think, late October or so. But here it's extending all the way out into maybe a little bit of early November. And we may be seeing that already in what's actually happening out there in the wild, in that, notable late season ignitions in recent history include the East Troublesome and Cameron Peak fires in 2020, and of course the recent Marshall Fire. It's about as late season as you can get. So there may be some season lengthening in the Rocky Mountain region. The same is true in the Southwest. The total increase over time is not very much. This is a very small vertical range here. But the period of the year when that range is high is longer. And we also see out here, you see maybe the beginning of a secondary season of simultaneous fire in October. And you can see this more clearly if you lower the threshold down of, not 24 fires, but 10 fires or 8 fires or something like that. This little secondary peak becomes more apparent. And that's a really interesting result, because changes in seasonality can have a big effect on fire management resources that are available for things like controlled burns, because often when one GAC is off season, they're sending a bunch of their equipment and firefighting personnel and things off to other places to go help manage things for controlled burns in those other regions. And the Southwest has an earlier season than most of the rest of CONUS. And so if they need their resources later in the season, that could have a big impact on how much sharing they're able to do with other regions. Moving into California, Southern California, as I mentioned earlier, here the absolute simultaneity levels are pretty low. A return level of only 10 or 11 versus 20 plus elsewhere, which is why this decadal plot is so noisy. It's just because the absolute numbers are smaller. So, there's a lot more room to bang up against the floor of 0. So there's still an upward trend, but this is a much noisier plot. And this also sort of shows signs of the season ending later, which may be consistent with other results that people have found of there being a sharpening of the wet season in this region, where, in the winter, they're sort of getting the same amount of rain, but over a shorter period. That may be related to what's going on here. And that's a result that's been seen in a number of different simulations. Northern California, pretty much the same as Southern California. The upward trend here is even lower. It's still an upward trend, but it's a very mild upward trend. Although it does depend on which climate model turns out to be most like reality. There's some of these models have a pretty steep trend. The ensemble as a whole has much less of a trend. But this region is also showing that same extension of the season and the season of when you might get a lot of fires happening at the same time, going longer and later into the year. Finally, so this is a visualization that shows the frequency of years where the peak simultaneity exceeds that historical 95th percentile. So these are years when the annual maximum of the median of the projected distribution exceeds a threshold. In this case, for Great Basin, it's 17 simultaneous fires. And what you see here is that, it's not like the future, you still have good years and bad years. A bad year, it's not like every year is bad when you move into the future. It's just that the bad years become more frequent and the good years become less and less common. You can also see, these are 5 different regional simulations here, and you can see there's a lot of variation and disagreement between them. But overall, this pattern of, the bad years get more frequent and the good years get less frequent as we move into the future is pretty consistent. And this is a sort of a very striking visualization that was an example of one of these some of this co-production that we did with the stakeholders, is that we had a lot of meetings with them. And this is one of the visualizations that was sort of developed iteratively in conversations with them, with a lot of, taking a lot of their input into account as we developed. This was a very popular visualization with the stakeholders. And, we developed it not on our own and just handing it off to them. We developed it together with them. So in conclusion, the big picture is that simultaneity in the Western US of very large wildfires is projected to substantially increase across most GACs throughout the 21st century. And that is going to impact resource sharing for fire management, which is important. The amount of projected increase varies significantly by RCM, by climate model, especially in the northern part of the US. Many of the simulations show a lengthening of the season of high simultaneity in the Southwest, in the Rocky Mountains, and in the California GACs. We found that the best predictors of simultaneity were Canadian Fire Weather Index and 100-hour fuel moisture over the entire Western US. That was pretty consistent. Please watch for another seminar coming hopefully in later this year from our whole team that's going to talk about the entire convergent fire project and a bunch of the different pieces of it and how they all relate to each other. So thank you very much.
Excellent. Thanks a lot, Seth. We've got plenty of time for questions here, so feel free to raise your hand or you can enter them in the chat and I can read them. So I think we have a question already from William Mahoney. Does this analysis include loss of fuels due to previous fires as the century progresses? What's the cause of the reduced likelihood for some GACs in the 2075-2085 period?
It does not yet. That is a question that we're sort of looking at and trying to figure out how we can incorporate that into, and that's sort of bridging the gap between the climate piece of this research and the ecology piece of this research. There are some stakeholders who are really interested in that question of, what's the vegetation succession and is that going to be affected by climate change and things like that. At the moment, we don't have that built into any of our analysis yet. We're not sure exactly what causes that dip in some of the simulations at the end of the 21st century. That's another thing we've noted and said, we need to look further into that. It may be, that there's one particular global model that is that has like 3 or 4 different, that is downscaled by 3 or 4 different regional models. And so if that one is doing something where it gets really moist at the end of century, that might be driving down, the entire ensemble because of that, the behavior of that one particular global model. But we still need to look into it more to be sure what's actually happening there.
Thanks, Seth. Good talk.
Thanks.
All right, Jackie Schumann, go ahead.
Hey there. Thank you. That was a really nice talk. I was curious if you could explain more about why you were specifically looking at the 100 and 1,000 hour fuels. The 1,000 hour fuels are traditionally left out of rate of spread calculations. And so, and fire, could you just talk a little bit more about why you chose those fuel classes? A lot of fires are driven by the small fuels, Marshall Fire being a great example of that. where it was the small fuels and the change, the responsiveness of these fuels to climate variability.
It's more that, well, so we wanted to use a lot of the well-known fire indexes. So we said, okay, we have to do KBDI and, Canadian Fire, and ERC is very popular with the stakeholders. They're really interested in ERC and burning index, and FM100 and FM1000 are things that go into ERC, so we had to calculate them anyway. So it wasn't necessarily that we thought a priori that they would be good predictors. It was more that we had them on hand and we said, well, let's just try all the predictors we've got and see what works well. It is also, FM1000 is also, an index that the stakeholders are very familiar with. And so, they're interested in knowing how it's going to change, not just in these statistical models, they're also interested in sort of just knowing how it's going to change on its own, because that they have all these intuitions and learned experience in knowledge of things that are based on things like ERC and FM1000. So if we can cast the climate change information in those terms, they understand it more readily than if we just use something like all our climate variables that we're used to. So.
Thanks.
Okay, a question from Sam in the chat. Who says, I'm curious as to why the models performed worse in the eastern and southern regions. Too much variability in ecosystem type, high influence of land use, including forestry and or urban areas?
I think mostly what it is just that these are very, very large geographic regions, and in almost all of the region, there isn't any fire. If you look at this eastern GAC, you can see that all the firing is happening up here and down here in the Appalachians, and there's very little of it anywhere else. And so it's just that if we take one of these fire indexes and we average it over the entire spatial region, you get something that's not well correlated with what's happening, in terms of fire simultaneity. We think that we would probably be able to do statistical modeling that was a lot better if we were able to focus on just these little regions, focus here and do a simultaneity model just for here. And, there's also things like Florida has a bunch of fires, but so does, Oklahoma and northern Texas. And those are very different in terms of their climate and sort of what's going to be happening climatologically in those two areas. And so we'd probably do a lot better if we were able to model them separately. And that's on our list of things we're thinking about doing. We haven't gotten to it yet. And, in terms of looking at the entire GAC scale, it's just, these guys are not sized well. These guys aren't climatologically coherent in a way that lends itself well to the statistical modeling at that spatial scale. We probably need to go to a smaller spatial scale to get good results there.
Great, and there's a follow-up from Pat Halbecker that I'll try to paraphrase, basically saying, is there some tension between subdividing into regions that might be climatologically related and losing statistical significance? Like, what's the ideal scale for y'all?
Yes, absolutely. What is the ideal scale? We're not entirely sure. There's also a tension in that these are, the regions we're using here are political. These are based on state boundaries and things like that, rather than on climate, regions or things like that. So yeah, like figuring out what the right unit of spatial analysis is hard. And, we might get more statistical power if we just sort of did it on the optimal climate. We could find optimal climate regions to do it on, but we do ultimately want this information to be useful in fire management decision making. So, if all of their decisions are happening at the GAC scale, we need to take that into consideration. And if we give them results that are based on climate regions that have no relationship to that, that's going to be harder for the information to be useful to them. So it's part of this balance of like, how do we get something that's mathematically and physically useful, but that is also meaningful to the end use, the societal end use. We have sort of discussed how we might do analysis on smaller regions. And yeah, I don't yet know what would be the cutoff where, oh, if we go too small in this region, we're going to lose all our statistical power and the models are not going to tell us anything anymore. That's definitely something that is a question, and that's something we're trying to figure out still. So if you have thoughts about it, we'd be happy to hear them. Send me an email.
Thank you. We also have a question from Joe Trivia, who asks, how would results change if improved forest management in the future were taken into account?
Oh, that's a really good question. And I don't think we know, but I think that is definitely a really interesting question that would be, we'd like to know the answer to that question. And the answer might be a lot. I mean, in particular, one of the questions is, how can people use this information to make changes that are meaningful? And one of the big ways that people might use this information is in changing ecological management policies. So, if they change their forage management practices, and that changes the frequency with which you have an overwhelming number of simultaneous fires, that's great. They would like to know, the stakeholders would really like to know if there are changes that they could make that would have that kind of impact. So that is definitely a question that we are interested and hopefully going to work towards. We're nearing the end of the first 2 years of the grant, and we're going to be trying to get an extension of it. And if so, that is, among the questions that we're going to try to start looking at in years 3 through 5.
Thank you. I had a question. So it was really neat to see how you use the learning type model to pick out the most effective indices, as, in these various GACs. Did you also consider sort of like a principal components or other type approach that would, compose an index of indices, or to think about the best combination of those and what was most predictable?
Not yet, but I think we might consider it, going further on. We might, in the beginning, it was when we were also looking at different matters of different types of spatial aggregations. This was like 900 GLMs per GAC. And so it was just a huge number that we said, okay, we're just going to look at one predictor. Now that we figured out like what the best individual predictor is, I think we can start, saying, okay, we've narrowed it, the huge space of possibilities down. Now we can consider opening up again some more and saying, okay, maybe a multivariate model would be even better than a univariate model in terms of fitting. Maybe the non-zero piece wants a different predictor than the count piece does, or something like that. There are also some other fire indexes that we're considering how to implement, and whether it be, whether we could calculate those that are sort of, in the same way that are built on top of, that ERC is built on top of 100-hour and 1,000-hour fuel moisture. There are some that are built on top of ERC and burning index, and so there are a number of composite fire indexes that are also worth considering. It's kind of a matter of like, how many different input data sets can we manage to run through statistical models before my laptop overheats and bursts into flame?
Thank you. Makes sense. All right, well, I'm not seeing any other questions. So let's thank our speaker once again, and look forward to seeing everyone for the seminar next week. Thanks a lot. Take care.
Thank you.